Oh, is this thing on? Oof. We got a cold one tonight in New York City, snowing everywhere. It's crazy, but today, I know why you clicked on this video. You want to learn how to optimize? I'll show you how. And welcome to the channel, Nitty Gritty Maths. As you know, I do have another channel, Nitty Gritty Gaming, and on this channel, we're going to do only math from simple techniques and from algebra to advanced calculus. We've got it all here. So today, I'll teach you some optimization and just welcome to the channel. So what is optimization? Think to yourself, if you're good at the subject, this should be really easy review for you. If you're new to the subject or you're not as strong in the subject, you might want to have a listen, learn. We're going to do an example, walk through it together. I'm going to give you another problem. You'll do it by yourself. I'll show you the answers at the end. So optimization. It's a mathematical technique for finding a maximum or minimum value of a function of several variables subject to a set of constraints such as a closed interval. So what it's saying here, you are going to find either a maximum or a minimum based on using derivatives, using other variables, more than one, and we're trying to use those variables, put them in equations, and make it for only one equation. So we're solving for one of the variables, plugging it in, finding that derivative, and knowing that the derivative for a maximum is 0, we can take that to our advantage. So the steps that we take when solving an optimization problem is that first we read the question carefully. I can't emphasize this enough. You got to read the question. If you miss one key component, you can't solve the question. You need everything. In math, everything in the question is vital. So the next step we have is to draw a picture of the scenario. Drawing really helps. And that's all I'm gonna say. You have to draw the problem. You're not gonna know what's happening. You can't imagine in your head. I mean, I'm pretty good at this stuff, but I need to draw it. You need to draw these stuffs out. Like some of them, you don't need to draw them, but even simple or hardcore stuff, you need to draw. So another step is label the lengths. If it says they're the same, then use the same variable. If they're not, you got to use a different variable. You cannot use the same variable. If they're different lengths, then you got to use different variables. So reread the problem, look back, and compare it with your diagrams and see if everything matches up. If that matches up, then you try to optimize. You find your equations, you write them down, then you see which variables they have similar, solve for one of the variables, and also create an interval, because we're working with shapes here and they can have negative value. You can't have a side that's -5. It's going to be pretty hard to cut -5 centimeters of something, and that's what we're trying to do here. We're trying to create an interval. We're going to set it equal to 0 since you can not cut it at all. For example, if you're cutting something, you can cut nothing at all or you can cut all of it off. We'll figure that out in the next example that we're going to show you. And using relationships between your variables from the extra information, rewrite the function to be optimized in terms of one variable. Getting terms of one variable, you can put in another equation and find the derivative of that. So the first example here, suppose you have 102 meters of fencing to make a 2 side-by-side rectangular enclosures that share one side. So as you can see over here, we have 2 rectangles side by side with their sides being adjacent to one another. They're connected, and we'll set both long sides equal to y, and because we can set the whole thing equal to y, both of those long sides and those vertical sides, we can call them all x since they're the same size. So the steps we're going to take here: write the formula for the perimeter. As you can see, the perimeter will be the 2 horizontal lines, the y's, that will be 2y plus 3x. Since we have 3 vertical lines, that will be 3x, and we're going to set that equal to 102 because that's the total amount of fencing we have. That's the perimeter. That's what we have to work with, and it says in terms of x and y, We can't use any other variable. We can't use the same variable because they're going to be different lengths except for the 3x's and the 2y's. So we wrote the formula for the perimeter. Now we write the formula for the area. The area formula will be x times y. Very simple. It's a rectangle, and doesn't really matter about that middle enclosure. That's only going to be dependent on the perimeter. The area won't change if you put something in the middle. So we can see that. Then we solve for one of the equations, the perimeter equation. So if you can't follow along with me, I'll show you in the next slide. There's the perimeter. There's r. We use a 3x plus 2y. We set it equal to 102 since we have 102 meters of fencing. We solve for one of the variables. We just minus 3x to the other side, divide by 2, get y equals 51 minus 1.5x. Then we use our area. We have an interval as well, where we restrict our sides because we can't use more than one of more fencing, so we can do that. And then we solve for one of the one of the variables. Then we plug the rearranged equation into the area formula. That's why we optimize. We solve for one of the variables. We put it right directly into the area formula. We put the y equals 51 minus 1.5x. We plug it back for y in the area formula of x times y. So x times 51.1.5x. We distribute the x. Then we find the derivative. And finding the derivative here, you guys probably should know, but we reduce the exponent by 1, bring the exponent to the front. That's all we do for derivatives here because we're working with just expressions. So on the derivative, we get 51 minus 3x. We set it equal to 0 since the maximum and minimum, if you graph it out, the maximum and minimum have slopes of 0 because they're the highest point on the graph or the lowest point on the graph. So that's where the slope changes. So that's why we can set it equal to 0. We can take advantage of that, put the 3x to the other side, add it, and solve for x and get 17. So your interval, you don't really have to think about it that much because there is a restriction here, but it has to be equal to 0, and it can't be negative numbers. So don't really stress the intervals out because just know it has to be greater than 0. So then we will just plug in the x that we determined. The x is equal to 17 meters. We'll plug that in to our y equation that we got from rearranging the perimeter equation over there. Y equals 51 minus 1.5x. We plug it in, get y equals 25.5. The original question said, what's the maximum area you can enclose? We say the area is x times y. We got y and x. And I switched them by mistake. The y is 25.5, the x is 17 meters, but the answer will still be 433.5 meters squared. So that's one optimization question. These are relatively simple, this type of optimization question, but the next one I'll give you some time to think about. Here it is, a rectangular piece of sheet metal with a perimeter of 50 centimeters. It rolled into a cylinder with open ends as shown below. Express the volume of the cylinder as a function of x. Find an approximate value of x that will maximize the area and find the maximum volume. So, and round to the nearest tenth when necessary. So I'll give you a second. You can pause the video right now, do the question, and let's see if we get the same answer. So I hope you paused the video right there, and now we're going to walk into how to do this question. So last question, I showed you all the steps, what we had to do. This one's going to be a little bit difficult since we have a cylinder here, but it's not going to be that tough. If you get every optimization is the same question, you're going to have the same types of question because you're going to have two shapes and you got to set them equal to one another by using the equation. So you're going to find the perimeter and the circumference. The perimeter of that sheet of metal is going to be just 2x plus 2y equals 50 since we have 50 centimeters to work with. So that's our perimeter, pretty easy stuff there. And the circumference of the top of the cylinder, since it's open, it doesn't really matter because the volume is still going to be the same. And the circumference, they told us the whole circumference is equal to x, which we can take advantage of because one of our sides in the sheet of metal is also x. So we can say C equals 2 pi r, or circumference. So we said the circumference is equal to x since it goes all the way around. X equals 2 pi r. Rearrange the equation and get r equals x divided by 2 pi. So we found the circumference, we found the perimeter. Then it says find the equation for the volume of the cylinder. we say the volume equals pi r squared h. You should know that equation. It's the equation of a cylinder, and it makes you know some of the equations. So you gotta know them, or you can't do them. That's one of the restraints here. But the volume, in the previous slide we said r is equal to x over 2 pi, so we can substitute the r squared and plug it in. We squared, so this step right here, the x squared divided by 4 pi squared, I just plugged in the x divided by 2 pi and squared that straight away. So, and the h here will be y, since we can see in the beginning in that picture the x is the circumference and the height will be y. So we defined that since the other sheet of metal will be y centimeters high. So we'll see that. We got the equation. That's part A right there. The next part is finding the x that maximizes the volume. So we're going to do the same thing here, but before we do the in the equation, we can see on the previous slide we solve for y because we got the perimeter. We used the perimeter. We did 50, we put minus 2x, divide by 2, and we get y equals 25 minus x. So we plug that into y there. That's how we got that volume equation. We use the volume equation, distribute our x squared divided by 4 pi times 25 minus x, and we will get 25 x squared divided by 4 pi minus x cubed divided by 4 pi. So we are going to use that, differentiate, and we will get 25x divided by 2 pi minus 3x squared minus and divided by 4 pi. We set that volume, the derivative of the volume function, equal to 0 since we're finding the maximum volume. We get, we're going to set it to equal to 0. I just added 3x squared divided by 4 pi to the left side, and I wanted to work with positive numbers here. Just cross multiplied and solve for x, and we got 50 divided by 3. That's to the nearest tenth, so we'll get 16.7 centimeters. So that's the x. And the volume, the maximum volume using that x, we're just going to use the original volume equation, the x squared divided by 4 pi times 25 minus x, and we are just going to plug in the x that we determined from this, plug that straight in, and we're going to solve for the maximum volume, 184.2 centimeters cubed, since the nearest tenth. And I really hope you enjoyed this lesson. Leave a like if you enjoyed. Comment down below what you want, other lessons you want to see in about math, because I really enjoy math. I mean, I can help you pretty much in anything you want, and daily content. And I'm trying to think, maybe every other day I'll post something on this channel. But don't forget to subscribe. Until next time, Nitty out.